Good afternoon, good morning, good evening, everybody, and welcome to this week's EMinar. Today we have Alireza Malehmir from Uppsala University talking about smart exploration. I'll give you a brief overview of his bio just before we start the talk. But before we do that, I'd like to remind you of the upcoming EMinars for the next few weeks. So next week we have Stefan Thiel talking about OSLAMP and the large-scale MT initiatives that are happening in Australia. And then the week afterwards, another Australian, Alison Kirkby, on MTPy and giving us a user's guide how to use it. On the 3rd of March, then, we have Doug Oldenburg talking about the fundamentals of inversion, and directly afterwards, on the 10th of March, Lindsay Hege, how this kind of knowledge can be captured in code, and specifically about SIMPAC and GeoSci. Then on the 17th, we have Constanza Manacero on a reduced order approach for probabilistic inversions of 3D magnetotelluric data. So I suppose that will be quite interesting in terms of future developments. And on the 24th of March, Juliane Hubert will talk about space weather and geomagnetically induced currents and MT. And then on the 7th of April, Nasser Makbel will talk about ModEM and also give a user's guide for those of you who are interested in 3D MT inversion but didn't have a chance to try it yet. And then at the end of April, we have Randy Mackey on geologically consistent inversion of geophysical data, a role for joint inversion. You can also find a list of EMinars on the MTNet webpage. I suppose if you registered, you know about this page and the table there. And just a very quick reminder that about the settings in Zoom for these EMinars. So the most important things are you can raise your hand in terms of if you have something important that you want to say in audio, or you can write things in the chat and or in the Q&A box. And I will monitor this box to see if there are any urgent questions, but typically so far we had most of the questions towards the end. But if there's something that is unclear, then please don't hesitate to ask. Okay, so with that overview, I'd like to introduce Professor Malehmir, who is, as I said, in Uppsala at the moment and is the current chair of the Near Surface Geoscience Division of the EAGE. He's the principal investigator in the Smart Exploration project that's funded by the Horizon 2020 program of the European Union, and that's what he's going to talk about today, but he has led several other research and industry-related projects in different areas of the world and published a lot of articles and is an editor of Geophysical Prospecting and Nature Scientific Report, as well as an active member of EAGE and SEG. So working on the interface of industry and academia. So with that, I'll stop sharing my screen and hand over to you, Alireza.
Thank you, Max. I suppose you can hear me, and presentation looks okay, and all good?
All good.
Good. So good day, everyone. So morning and afternoon. It's really my pleasure to give this talk on behalf of the Smart Exploration team and to be with the EM community. I think most of you are from EM and MT community, and I'm very glad to be here. And I thank Alan for inviting me to give this talk. Just before I kick the talk, I just want to make sure that you know that the presentation, some of the material I present are not all done by me, and there are many who have contributed in these materials and work. So hopefully I have acknowledged them in their respective slides. If not, I apologize already now. So where do I come here? So I'm actually not a really totally EM or MT person, but I've been in MT and EM fieldwork. So back when I was a PhD student at Uppsala University, I was asked to go for a MT survey, and I heard Juliana Hubert is giving a talk in a few weeks. So she and we went to an MT campaign along a seismic line we acquired earlier. And this is a section from then showing, down to 12 kilometers of cross. We saw a package of reflectivity that was associated with conductive material, and this provided us some clue that we were likely looking at metasedimentary rocks that have graphites. And even then we had these fingers, the Christianberry mine, which is a major VMS deposit, around 10 kilometers into the plane and into the monitor and to the east of this section, essentially projection where the arrow shows. And then we were hoping this package of diffraction that we were seeing in the seismic data would be associated with something, but we couldn't really nail it down. We did see a very nice conductor sticking out like this one, but we couldn't really convince ourselves if we were seeing the same thing. And of course, 3D effects, and these are some of the things I would be talking. What I realized then was, MT is as tough as seismic, so you have to dig for your cords, and the cords we had at Uppsala, they were really heavy. I think at the time we couldn't carry more than one coil, and this picture just shows, we went to a site to set up an MT station. Just on the way back, it rained so much that our bus went into a ditch, and it took us hours to first empty the bus and then try to rescue this bus, and we couldn't rescue it. So really, there's quite a bit of a potential in doing seismic and particularly MT at larger scales. And a little bit of a shame that this is not what I would be mainly talking. So it would be a bit of a seismic, but there are also EM components in my talk. So here's an outline. I would be talking why we need to explore for minerals. And of course, this is not hidden for many of you. We're now entering into an energy transition. So, and the mineral is going to be likely a big thing for at least the next decade. I will talk about the 4 cornerstones of smart exploration and what the smart exploration is about. So these 4 cornerstones are looking into legacy data, existing data. I will introduce the prototypes, and we'll look at 2 of them in details. You will be looking at some data, some new data that we have acquired, particularly what we call sparse data, not cutting, not clearing forest, for example. And I will introduce shortly 2 of the EM modeling algorithms that comes out of the smart exploration, and I will end up with a summary. So just to put everything in a context. So if you look at, for example, from this graph, this plot, everyone else, then Europeans are producing, and they're producing raw materials. And let's say we're not talking about woods or fish, but well, we're not talking about woods. We're talking about metals and minerals. And when we did a survey within the smart exploration community, which we think most of these people are experts, they're geologists, they're not like public people, geologists, geophysicists, people in this business. Most of them blame social acceptance to be the main hurdle of mineral exploration in Europe. And some also blame unsuitable geology. And maybe you can, to some degree, agree with this. Of course, you have in South America, Latin America, and I know part of Asia, you have these big deposits, and maybe you don't find them no longer in Europe. But I would say really this is kind of an excuse for not doing successful exploration. And these components are there, but I think we are still unsuccessful because we're trying to maybe take the same way of exploring different places in Europe, and it would not work the same way. And in Europe, you're dealing with lots of, if there are any big deposits, are likely going to be at depth. So you're really focusing at deep exploration. And And this would not be the case, for example, in Latin America. So in a way, Europe was, and I think it is still, let's see in a way what happens, and we can still outsource. We will likely outsource for some commodities. You would be likely outsourcing from some commodities from somewhere else. But I think to a very large extent, everything is outsourced in Europe. And of course, this is not acceptable because you have to deal also with your own backyard. So your backyard is also a backyard, and when we talk about doing everything clean and going towards green technology, you need to also explore at your own backyard. And not just exploring for the so-called critical raw materials for the EU, which are mainly like high-tech minerals or elements, like rare earth elements, REs, but also, like we still talk about iron price now is rocketing in a way in terms of price, and I think it's going to be some of the others like precious and even like gold, they have very high commodity price these days. So, and so the message, I guess, is that we can't really just blame ourselves for social acceptance because we're not doing a proper, or we're not doing a successful exploration. So we really need to also come up with technical and ethical solutions, like acting like a role model, how to do this. And then and this was the main message from our project, that we're going to act at least within the size and frame that we're able, the resources that are available to us. We will act as a role model, and then we try to introduce solutions that are going to partly tackle the mineral exploration in Europe. So Smart Exploration was launched in 2017, so 27 partners from 9 European countries, so 11 of them, you can see it in this map. The green regions are where or partner countries are, or partners are located. Essentially north, south, east, west. So we have partners from Portugal, Greece, Central Europe, Northern Europe, Finland, and Sweden. So 11 research and development institutes, including geological surveys, 11 what we call the small and medium enterprises. These are tech companies, and 5 stakeholders, so mainly mining companies. In one case, we have also Ludvika community, which is essentially a municipality with us in the project. We have 6 exploration sites that we can actually test our solutions, and we have access, we have generated data for our own solutions to verify our prototypes, and these are the location of the sites. The project is primarily research innovation. That means we're generating solutions that have market potential, and they reach what we call TRL, targeted readiness level of 5 to 6. So meaning that the solution have been verified or validated at least at one relevant exploration site. So just to highlight, if I don't catch up with most aspects of the smart exploration, so we have so far secured 2 patents in the project. We have plus 25 young professionals in the project. The project has produced over 100 peer-reviewed publications, over 100 presentations. We have 5 prototypes and 6 algorithms that you can actually name them. The example I show you today, they are from Ludvika Center, Sweden. They're from Nefskurvo, which is a VMS peering region in Portugal, southern Portugal, and then Gerolokos in Greece, which is a bauxite deposit. So in terms of how the smart exploration looks like, so if you think of research institutions and tech companies, SMEs, and stakeholders, this is how you can put them. So essentially research institution, they would likely, they would be helping with the instruments, so scrutinizing the instruments that the tech companies are providing. And then they're being validated at the exploration sites, and then again, research institution will look at the data and then try to explore what has come out of these prototypes, for example. And this is how the partners will distribute. So, and in terms of the key elements of the project, so as I mentioned, so legacy data, prototypes, new algorithms, and a lot of focus on young generations, young professionals in this project. When you're collecting data in Europe, on contrary maybe to, Africa and some other places in the world, you would be dealing immediately with cities. So you would be dealing with noise from the city, noise from, infrastructures. And one of the big issue, for example, on seismic data acquisition, which I'm pretty sure you also have it in AEM, is the noise and how to deal with the noise. So one of the solutions that we had earlier, and we tried to explore in the smart exploration, was to use, I guess you're familiar with the idea of interferometry. And that's if we can actually overcome noise with seismic interferometry. For example, one way that we managed to improve our refraction static solution, and that is to essentially estimate the overburden thickness and velocity and take it, compensate or correct for it in the seismic data. One way to do this is to, of course, to do typical refraction analysis. And for that, you need first breaks. And if you don't have good quality data, you don't have good quality first breaks, so you won't be able to get a good static solution. And once you not having good static solution, you're not going to get good images in the subsurface. So what we did back before getting into a smart exploration was we tried to explore using seismic interferometry, and essentially how you do it is for a given pairs of receiver recorded for one shot, you would do cross correlation between these two traces, and you will end up getting what we call virtual trace between these two sets of receivers. And then you could do that for many sets of shots, essentially all shots fired in these two sets of receivers, and sum them. That would be one way to generate very, let's say, improved quality virtual trace of the first break. And you can then repeat that and convolve this for many source location. And then you can basically go from a virtual trace, then now you can actually locate what kind of a source is contributing, but just convolving this trace that was recorded with a virtual trace. And that way you can actually improve the quality of your first break. And we did that in, for example, one of the sites in central Sweden, where we went into a abundant open pit with lots of infill material. So infill material, then the line went immediately into the city, and lots of, this is a brewery, and at the time there was a big dispute if there is a brewery fault or not, if the mine opens up again. So our goal there was to image the brewery fault, which we never did it, and we haven't done it yet, but we managed to get actually good quality data then. So this is typical seismic quality, shot fired somewhere in the pit, abandoned pit, but you can see the first breaks, they don't go anywhere. So it's, you don't see the offset, but this line is about 2.5 kilometers. So you don't see anything beyond 200-300 meters. And if you do what I just mentioned to you, you start working with a virtual first break or a refraction arrival, you can actually improve the first break. Now you can actually see the first breaks are continuing a bit longer, and then now you can actually pick it, and then you can estimate the static better. And that's what we did. So in this example, so another shot record, this goes to the city. You see it's a very poor quality data because of all the source of vibration in the city. The effect of the pit in the first breaks. If you just use the data for a static solution, this is what you would get. So as a proxy, you would look at the continuity of the first break. So it's, in a way, it looks like a decent static, but we don't see any clear reflections. And if you use the first break the way that I mentioned through the interferometry approach, and then do the statics, now you can actually see them maybe a nice reflection lining up here, which is kind of there, but you would not guess it from this solution. So it's way better seen there. So if we pass that into a smart exploration, some of these experiences that we got handling hard rock data, and we try to get very easy to use software that can, you can just put the data in, you can do the seismic interferometry quickly and get the statics. And this is one of our sites in Ludvika, where the reflection you see here is from the mineralization. And so this is refraction static corrected already from the data itself, the real data. And this is when you add the first break, the virtual first breaks. And now you can see even the continuity it's a bit better. And we're talking like this kind of level, that little improvement actually will end up to be a significant intersection. So you can see the continuity of this reflection, which is from iron oxide mineralization, is way improved. And that is at the number of peaks from the data. You could say maybe raw data or the data without interferometry, and this is with interferometry or super virtual traces. And now you can see you gain quite a bit of a first breaks, and this contributes into better static solutions. Our partners at University of Technical University of Delft, they managed to turn seismic interferometry, they reformulated in a way that instead of now improving a first break, they could estimate the surface waves, and then they could try to remove it. And that's an example, again, the same data set from Ludvika. You can see a row shot gather, lots of surface waves going here. And these are actually also typical, lots of surface waves we see in European data sets, and I think it's the same in Canada. And now if you formulate your interferometry that would target, it would basically regenerate the surface wave, re-estimate it from the data. This would be the surface wave estimated through the interferometry. And then now if you remove it, this is how you get the reflection image. So if you just go back and forth, you can see this reflection, which I had to beg you to accept this. Now it's way better seen after we have removed it. We have removed the surface waves. Through solutions like that, we managed to get initial sections like this. So this is a 2D section now from Ludvika, where the target mineralization is iron oxide, magnetite, and hematite. So the reflection section you see, it's very, very nice. The borehole you see is as much as we can see. So there's one deeper borehole that comes here, hits the mineralization at 800 meters. So you can see now through some of our algorithm, we are able to image the reflection from the mineralization, not only see, compared with the ore block model, but rather suggest that it may continue towards depth. So for another 300 meters. But remember that we're looking at the 2D data, and I mentioned already that you really need to be careful when interpreting on 2D data, and this would not be exception. So sometimes you can see reflection extending beyond what they are because they're out of plane. Sometimes you can see them shorter than what they are because the way you have collected data. So, and that's really a 3D footprint. So, and one should never drill or put too much interpretation on 2D data. I come back to this Ludvika data set because we require a 3D data set, and you're gonna compare some 2D and 3D and see what one can learn. But before going there, at the Gerolaikas, we also look at some of the existing data, what we call legacy data, historical data that we managed to recover. In Gerolaikas, the problem was that the bauxite deposits, they disappear. And these regions are actively tectonically active. So we're talking about Greece, and it's a really, you have lots of seismicity. So what we did that we built two scenarios that, from the structural geology data, we knew there are lots of downfolding, normal folding, and, horse and graben structures, as you can see here. We didn't know how deep this bauxite deposit, which are these orange lenses, they're downfolded. If they downfold, like let's say below sea level, they're unlikely going to have any, this horizon, for example, would unlikely have any bauxite deposit. And I think this is something to do with oxidations and the way the bauxites are deposited. And if it's only downfolded a few hundreds of meters, then there's a chance. So what our guys did at National Technical University of Athens, together with our partners there, they built scenarios. So two scenarios: downfolded very significantly down a few hundreds of meters, downfolded just a couple of hundred meters. They built a velocity model for the two scenarios. They made a density model from these two scenarios, and they inverted and they look how different these are. But they couldn't actually rule out any of these scenarios until they went in and they set up seismometers. And because the region is tectonically active, they have lots of earthquake, micro earthquakes. So using a setup, I don't remember now in my head, but I think 400 stations, they managed to record over 3,000 local events. These are shallow events rather. And around thousands of them, they met their criteria and they were used for estimating the velocity. So you can actually see the event as they were recorded in the array, and the array actually is shown there. In a way, this was very genius because given that the sources are under the region, therefore the ray path to the stations are rather straight, you know, one could estimate very good velocities from doing travel time tomography, essentially, you know, this traditional travel time tomography of earthquakes. And then we were lucky that there was a hydrocarbon seismic line shot in the area, and this was the result of the legacy data. We got it as a paper copy, and you know, I look at this, I don't believe you can interpret anything on this section, and when I saw it, I said, well, you're in a carbonate rock, so maybe, you know, you don't get so much good sections. And it's so bad that you shouldn't even do seismic in this area. So, but once our guys, they managed to get a velocity model, they did pre-stack what we call depth migration, just using the data, and then they reprocessed it. You know, now we know how to deal with hard rock data. And okay, this is a carbonate, but it's still kind of a hard rock data. And now you can actually see, you know, there seems to be this is a carbonate that this bauxite sits under. It seems to be downfaulted here, but it's not a so clear image. If now you use instead the velocity that you derive from the micro earthquake, this is the velocity model, and that's the image you get. And it's way better. It's way pronounced. Now you can, you know, nicely say this horizon, as I said, which above it is you have the bauxite deposit. It's only downfaulted for, let's say, a 300 meter, and it appears to be above sea level. Don't look at this scale. So it's actually after or imaging, this will be your sea level. So it was very promising, you know, to recover this data, to complement this with this, in a way, passive seismic, but use the passive to retrieve the active data. So let's look at some EM stuff, perhaps. So the project also developed 5 prototypes, which we are very proud of. One of them is a GPS time transmitter. I will open up why we need that, and I think there may be a space for EM community in this. So a GPS time transmitter was developed for array of sensors. It's not a point transmitter, let's say, or for point GPS antenna, for example. We developed electric vibe that is broadband, so it's not hydraulic. And it has a true broadband frequency, you know, it's very reliable. Our partner at SkyTime, they developed their system to 6.25 hertz. So maybe you heard about this. I will not focus on the SkyTime development. We also developed a Steamhold system for NQ size boreholes. This is fully digital system. It's modular. You can actually add sensors as you wish. So the data transmission, it's digital, so we basically use fiber optic for getting the data up to our computer here. And then you can see a test that was done last year at the Ludvika site. I would talk a little bit more about the UAV ground system, especially the EM component of this, which we're also very proud, and it's work done by SU Uppsala University and AMCVO. Just getting into the UAV system. So, of course, UAVs are very, you know, very interesting. Many people want to work with UAV system because they're light. So you can see they're not going to replace, let's say, fixed wing helicopter, some of these measurements. But if you got a target at intermediate depth, if you got an area which is logistically challenging, you know, you can't fly, you can't rent helicopter, you can actually easily maybe ship a drone. And this, you know, instrumentation is way lighter here, so you can use this for your exploration. So the system developed in our project, it measures the total field. So of course that's the easier part. We wanted to also make this modular, but you know, within the 3 years we couldn't make it so far. So so we focus on 2 major components: total field magnetic. So essentially 2 sensors, 2 birds, one that just carries the magnetometer for total field measurements, and another one would be a 3-component induction coils for broadband electromagnetic, so control source and radiomagnetology. So we call this extended VLF band, so from 1 to 350 kilohertz. And you can kind of see the idea. So we also wanted to make one acquisition system in a way that if you don't want to do UAV survey, you can actually do a ground measurement. So it's you could think of it like this way also, like one shot, 2 birds. It was the idea. And we have also very quick on-site data visualization and modeling, so you can decide whether you want to change the site. So let's look at some of the features of the UAV EM, let's say, system. As I said, we also have a MAC. So we started with quadrocopter, and you can see we did quite a bit of a test. And the problem with UAVs is the noise from the UAV and how you can overcome the noise from UAVs. While you still have the sensitivity and you manage, with the logistics flying, you don't have so much long cabling from the UAV to your sensors, because this will also add its own problem. So the EM system has 3 induction coils, as I said, three components, magnetic field measured, and the other one is just total field magnetometers. And these are some of the features. Before we went too far, or we went very far, we decided to test different UAVs. And we're lucky at Uppsala University, we have a shielded room that you basically are shielded from external EM, and I think it's also seismic from shaking. So if you want to talk secret stuff, you can go to this room and nobody can hear you. And so this is a shielded room in Uppsala. You can see, I think this is at the time is a quadrocopter that was tested. So our idea was to test all these drones that are available and study their induced magnetic field and EM field. This is also another test that we did outside. So I think this is the induction coil. So that's a turbocopter. So that's a diesel driven, I guess. That's a hexacopter. This is something we developed at the end, custom built. And you can see some of the DJI drones also here. So just to plot below, you see frequency spectra of different data sets. The blue here is a background, so that means none of these were above the induction coil, and the red one is a turbine, and the purple line is your DJI. And you can see that by far the turbine turbocopter is the best, but we couldn't see this practical, so we ended up building our own hexacopter where we had control on the electromotors and the setup, so we could kind of shield as much as we could components that would induce noise into the measurements. So we ended up with this hexacopter. So that's the bird. Lots of 3D printing went on. So at some point we wanted to have it light, but we also realized it became too light, so we started adding weight, because then it was not possible to get a very nice consistent fly. So here's a picture from one of the surveys. I think it's Ludvika, and let's look at some data. So that's blood barrier, iron oxide. So you can see it's beautiful, magnetic. So it's no question. So the reflection I was showing you before, it's from this blood barrier. So it dips down towards southeast. Our team from SU, Uppsala University, OMCO, they went in the areas. We have 4 actually data set, 4 airborne mag data set in this area. So we have one fixed wing from 1972 flown at 30 meters above surface. We have a SGU, Swedish Geological Survey, or Geological Survey of Sweden. They flew 2016 again, but this time they went orthogonal to the strike of the mineralization. So we have another fixed wing 2016. We have a SkyTem. They flew in the area for the 6.25 hertz, but of course they also collected mag. And then we also have a UAV that was required in the area. So the background line you see is a 2016 of SGU. And these lines are the UAV. And of course, you would have to have a landing site. You do have regulation that you need to have you need to have eye contact with your drone. So, and this regulation still is in Sweden. So you can't really, decide to fly very far. So, and that's one of the, of course, shortcomings of drones today with the current regulation. Just first look at some MAG, and then we'll look at some EM data. So these are the 4 data sets that I mentioned to you. So they've been all corrected in their own way. So I think this is the reason we have some shift. Of course, they have also been collected in different years. And that could also partly contribute to the shift. But what's very interesting for us is, of course, they resemble very nicely each other. So these are point co-located. But what's more remarkable is that the UAV MAG picks more picks. So, and in the area we have 2 lenses, 2 major lenses. One is magnetite rich, and one is it has some hematite. Essentially, it has lower magnetic intensity, and we can nicely see that in UAV measurements. And our interpretation at the moment, and I think it's consistent with the earlier measurement that we did in the area, is that the fact that we can actually sample, or we fly, let's say, with a lower speed with UAV than fixed wing and helicopter, you can especially sample more. Therefore, you're able to spatially resolve better features that you have. And I think this is likely what's happened here. And we nicely see this in the UAV. This fixed wing 72 is actually seeing it too, but not so significant. If you look at other places, even fixed wing couldn't see these two picks. I think most of you are interested on the EM components of this. So at the same time, our team, they were of course able to measure for radio magnetotelluric frequencies while flying. So with the second sensor. So the figure you see to the left is VLF, apparent resistivity derived from fixed wing VLF acquired by SUU. The one you see to the right is apparent resistivity. So sorry for this case. So red is low resistivity, blue is high. And I think MT community likes this kind of color. So blue is high, well, it's high resistivity, yes. So essentially conductive and resistive. So, and this is what we get from the UAV system. And if you see, it's very nice correlation. It looks like we see more level of details also. And we were very happy. I mean, our partners from doing this task were extremely happy to see this result. If you want to find some detail, you can just go to the first break issue of August last year, where we have detailed the prototypes, and the examples are shown there. There's some pictures. So is it only like radio magnetotellurics, or let's say passive sources? No, we also have our own ground dipole source here. So this is now the UAV system with a bird flying in the area, while the ground dipole used to essentially transmit lower frequencies. And so it's just pictures from the experiment last year. I think it was September last year or October last year. And if you look at some of the frequencies recorded in this sensor that is mounted in the bird. So that's a base frequency of 1 kilohertz. I'm assuming it was transmitted. You see very nicely all the odd harmonics in the data. Of course, you don't see it. I think this is just a direction of the signal being transmitted. So it's favoring more this direction. And I think this is H. So HX, HY, HZ, so vertical component and the 2 horizontal components of magnetic field. And yeah, so you see very nicely all these harmonics. And the bird was about 3-4 kilometers away from the source in this case. And this is 2 kilohertz base frequency, and now you see again the old harmonics 6 and 10 and 14. So really functioning, it's giving recording very nicely the frequencies being transmitted in the area. Stay with me for another 15 minutes. One of the earlier on, like I think it was 2016, we were asked if we can using seismic, if we can image vertical fracture systems. And Sweden has a site called Esbo Hard Rock Laboratory, and this was meant to test different solutions, different ideas in the hard rock, and especially for nuclear waste, storage. So we were asked whether we could do it. So then what we proposed was, at the time we developed 3-component seismic lander streamer, digital MEMS based. And we said, okay, maybe we would see it with the converted waves. So we went there and then we tried this for the converted wave, but we were also smart. We said, okay, if the fracture system are hit by the tunnel, we can do it like what MRI guys are doing. So essentially, that is, if you scan around your object, then your vertical fracture is no longer important. And having tunnels, having ramps in the subsurface, and being able to simultaneously record on the surface and in the subsurface, you basically overcome lots of these challenges. So what then we did, apart from collecting also then some lake RMT and ERT stuff, we also deployed wireless recorders on the surface and geophone planted on the tunnel floor in this part of the tunnel. And we simultaneously shot this. So in a way that we were able to, for example, from shot and receiver going in this angle, we were able to image this vertical, almost vertical fracture zone. And you can see it's very nicely looking here. But we could do this because we were able to park a recording truck outside of the tunnel and then have a GPS, GPS time stamping and sampling from the satellites by being exactly outside. And then the viruses were going, passively. So by having active sources, having a time of active sources, we could merge the data and treat them as one data set. But then we realized that this is going to open lots of opportunities, and I think even for the EM community, this should open a space. We don't know yet how we could do this, but I'm pretty sure you can, for example, look at the signal quality as being recorded down in some of these tunnels, and try to investigate your assumptions of a skin depths and all those things you do. And we said if we can come up with something that we can transmit GPS time in closed spaces for array of a sensor, this will make it very practical, and we can address lots of challenges and open new possibilities. And we were lucky, so of course we came up with this idea. We managed to make a Swedish patent out of it because we know lots of underground mining in Sweden, so we thought this will give us one level of protection. And then we went to Nevskorvo, and then we found beautiful setup. Lots of underground mines have parallel mining tunnels, and they have exploration tunnels. So it's really perfect setup for exploring below the tunnels and looking around the tunnels. So with the GPS time transmitter developed in the project, and also with the eVibe, the seismic source that I mentioned, we were able to acquire a semi-3D, essentially 2D line on the surface. And then 5 exploration tunnels were instrumented. They were shot simultaneously. So we had 1,300 receivers in this setup. And so you see a surface array here. We even brought these wirelesses you basically use on the surface. So now you can actually transmit time to them. So you don't need to modify your sensors. We made this a possibility. So this is how the setup looks like. So 2 receiver lines on the surface, they operate passively, and then receivers in this exploration tunnels. The idea was to look at down deep continuation of a Lombador. Essentially, you would be having this exploration tunnel as you drill down deep. So you look how this mineralization is extending below your exploration tunnel. So, but we use them for imaging purposes. And this kind of setup is way better because you can be in the tunnel and look around the tunnel. But since now you can shoot between them, from the tunnel to the surface, in the tunnel, from surface to the surface and in the tunnel, you can actually now get a better velocity model, better grasp of what's happening between the tunnels. And therefore, you can get better images. So this is some pictures of the cable system here, wireless, in one of the middle tunnels that I was showing. And that's an eVibe And we were actually very happy because we realized that we could not use any other sources in this particular case due to permitting issues. Of course, when you're in the tunnels, and especially operating mine, you're not the only one vibrating. So everyone else is drilling. We were unlucky at the time. There was a raise boring. These raise boring systems are huge. You know, it's like a 2 meter by 2 meter. If you hear them in the tunnels, you would be really scared. So one of these was actually operating also next to us. But regardless, we got very nice data. I think this says by itself. So this is the shot fired in one of the tunnels. I think it's the perpendicular tunnel, GP, yeah, so GP35 we call. And you can now see the timing. These are the surface line collecting. Of course, you see the first break, and in some of the other tunnel line, you see, we think these are reflections seen, and it's actually very beautiful. And now let's look at some results. So this is coming out of geophysics. So the EMinar array is already out, and the surface array has been accepted. I think it will be out within a couple of days. So it's surface lines, so it's around 600 meters. So there's no way you can cable your GPS transmitter here. So it's logistically impossible. So this transmitter that we developed really came handy. So that's the line that we wanted to instrument this longer, but the fans were not working in the tunnel, so we were not allowed to be there. So we came a bit short here. So around 800 receivers here, 350 receivers on the surface. We got access to some earlier data, so we knew that this guy, Lombador, it's a very big world-class deposit, so 150 million ton massive sulfide sitting there. Yeah, I think it's still sitting there. So you can see a beautiful signature of the Lombador. So this was a data set fired in 1996, reprocessed in 2007 by X company. So it became available to us. We reprocessed it in our project, and we got way better images, as you can see. So that's unmigrated, what we call a stack section. If you migrate, you see a beautiful signature of a Lombador deposit here. We got also some of the structures image. That's not the focus now. Let's look at the tunnel data or surface tunnel data. At the moment, we haven't imaged both data set together, and that's something likely would be part 3 at some point. So you would see them independently, but somehow connected. So that's the line from, that's a section from profile 6, migrated using the guess, or best guess from the data. Now, because you've been shooting and recording between the surface, you can actually get a very good grasp of the velocities. There's some footprints of the tunnel there. If you smooth out and get it a little bit more realistic, and if you redo the again migration and imaging, you can actually see it's way better. Just go back and forth. This is now using the velocities that we retrieve between the tunnel and surface. And that's when you just use the data. Now let's look at the 3D setup between the tunnels. So you can immediately see a beautiful reflection image here from Lombador, and has much higher resolution. It should have higher resolution because now you are close to the target. And you can see the strike of the mineralization seems to be 2 sets. Maybe we're seeing the thickness there. I don't know now. And that's Lombador. It's a bit of a not perfect match. I don't know why. While you are in the subsurface, even though you think you're solving quite a bit of a problem, you're also adding another problem. And that's now you are measuring in the subsurface where, if you measure on the surface, you're dealing with 3D problem from geology. But now if you go in the subsurface, a 2D geology can make 3D trouble. So, and that's something you need to be very careful. So we did quite a bit of a modeling from what response it's likely possible from Lombador, and this is very well defined from drilling. So what you see the dot is a reflection response on from Lombador into a section, so you can be very sure. But what's very interesting to know is that even though your seismic section is here, you're likely going to get reflection off the Lombador into this section. And the longer continuation of this, it's a bit, you need to be a bit worried that it may not be actually real. And it's essentially, it's a 3D effect. So you're imaging off plane. And we knew this, I work on a data set from Canadian, from Half My Leg. And there we realized that the 2D line picked up an anomaly that was 700 meters away. And it came deeper because it's away. Of course, it comes in time later. So that's something you need to be also careful. You image something that could be interesting, but because it's so deep, the company will not be interested. But then you're not accounting for this 3D effect. So essentially, 3D would come shallower, and it did come shallower, and it was drilled later based on the 3D data set. Saying that, we also went to our own area, Ludvika. We collected a 3D data set to just make sure 2D interpretations, we verified the 2D interpretation, make sure that, we understand what's going on. But we did not do any cutting. So we decided to do a new experiment to, no cutting, use all forest tracks, forest roads. We instrumented everywhere we could. So the red would be receivers and sources. Blue would be only receivers because we couldn't take the source. You can see it's a very narrow azimuth, but we intentionally planned this because the mineralization, which you can actually see this red and blue, they dip this direction. So this azimuth is very nice illumination angle. What we did not realize, and later we realized, was a lot of built up areas here, they sit on tailings, historical tailings. And that's another challenge that you have in European side. A lot of things been built up that you have no clue. And we're lucky that we have very high resolution LIDAR data in Sweden, so we could actually really see it here. But regardless, we got a very good data set. So very sparse data, but already in the short record, you can see reflections. If you clean up, you beautifully image these reflections that are from mineralization. Now let's look at some sections. So we start with a 2D. So we thought this 2D is just a 2D. You need to be very careful, as I mentioned. So some of the interpretation from before. Now you're looking at a 3D cube. This is non-migrated, but you can already see the mineralization looks comes. You have a lateral extent for it. There seems to be two sets there. If you now migrate, that's the ore block model. That's the deepest borehole. That is historical. This is by itself a questionable, actually. The seismic here is even verifying whether there should be mineralization or not. You see the mineralization. We see a reflection cross-cutting. We see disappearance or displacement of reflection here. And we tried to pick up high amplitude areas, match them to the boreholes. We picked surfaces from areas that we thought there might be structures. And now we estimated, so the ore block, now this is our estimation of how much likely iron oxide deposits are there that needs to be verified and drilled, at least to the extent of the seismic volume. You can see beautiful reflection cross-cutting. We think that reflection, I come back, that reflection there, it's kind of controls the geometry of this mineralization. Our partners developed also a solution to look at backscattering of seismic wave for places that we have discontinuities, where we have fault system, geological contacts, for example. You see one of them hits nicely here, very, very strongly. We do not just do seismic, or we did not just do seismic. So the seismic was used to essentially build model, reference model constraints were used from boreholes and downhole logging data. And we've verified that whether this extension, the potential resources that I was talking, they make sense with respect to magnetic data. And we did that exercise in our project. So reflections were used as a constraint, boreholes for a petrophysical constraint, and also for locations where we have the mineralization. We built a reference model. We inverted the magnetic data in this case. And if you use the threshold, you can actually go back. So essentially, the model that we have, it's consistent with the magnetic response that we observe in there. 2 more slides and I'm done. So we also developing, apart from all the seismic solutions I mentioned, our young professionals are developing also EM solutions. So 2 particular EM solutions, one on transient EM or time domain, or partners from Aarhus University, of course, they're keen on developing 3D finite element solutions that are useful for, what you say, like a coarse flight line spacing. So a finite element that the forward solution is 3D, but the inversion is done, I guess the modeling is done in 2D. And this has come out. So there's an article in First Break, well, I think it's coming now. So that I invite you to also look. They've been also looking at IP response, but I do not go into this in this presentation. Or people here at Uppsala University, they're also looking at control source EM. This is a frequency domain EM, and trying to also develop solutions. So again, based on finite element, I think the way they're doing it here is it's in a way is a bit of smart way. That is, you basically discretize your model. You use tetrahedrons, kind of in a how do you say, objective manner. So you go around your target smaller, and then when you go away, you use bigger. And this is done in the inversion and in the modeling procedure. And Paola, I guess she's also with us today. So she's working in this modeling work. So just at the last slide, I would say I think a smart exploration, try to demonstrate that you can still do mineral exploration while keeping all the social acceptance in mind, but then be a role model. So be innovative, look at the existing data, and work with young professionals and seniors together, and make sure the solution that you're developing will be used. And I have this for Alan. I don't know if he's still with us. So he said to me, make sure you spell electromagnetism correct. And I said, okay, at least in our project, I think, I don't want to self-praise ourselves, but I think we try to spell out a little bit exploration geophysics for mineral exploration in Europe. So it's lots of projects with geologists, geochemists, nothing wrong with it. But geophysicists, I think it's, need to also find their corner. So, of course, we need to do much more smarter exploration and include more of Maxwell equations and MT in this. I thank you for your attention. Sorry, this took 50 minutes.
Yes, thank you very much for this interesting talk. And the floor is open for questions now. And we actually already have a couple. So the way this works, I will read them out, and we also have them in the record, and then you can answer them. So we have Kayla Crosby. In the UAV airborne survey, what is the area of the transmitter on the ground compared to the footprint of the flights?
Very good question for my EM people. And I think, as far as I know, so I can pass this question to our EM people to just be accurate. But as far as I know, they did study the near field effect and all those things. And you could see that I mentioned that the transmitter was around 4 or 3 kilometers away than where they flew. And if you look at the area that I showed, that's very small. So I think they did all the math, and of course, from the resistivity of the ground, they made sure that they're not in the near field effect, and they would not have a severe footprint.
Okay.
Meredith is saying they might have some near field effect that they will have to deal with it.
Yeah, and I mean, that's always sort of a question in these surveys, but yeah, if you set them up carefully, you can deal with that.
So yeah.
There's a second question. How do you get to transmit the GPS signal from depths underground in tunnels?
Now we have some protection, so we can actually talk. So essentially, we don't cable, and that's actually, you could do that if it's possible. And that is, look, you have antenna, you cable it down to your location, and then you have what do you call, you have a amplifier of something and you transmit. That's not what we do. We could do that, it's not a big deal if it's possible, but this was not the intention. Essentially what we have, we use clock. So essentially you have a crystal that you lock a GPS signal into the crystal, and then we have simulator that they transmit GPS time signal as if this is sent by satellites. Essentially they follow the same protocols as satellites. And this, we have done the test that they have accuracy up to, I think for a day, 16 hours, because in Nevsko we were there 2 shifts. For 16 hours plus 16 hours, you have accuracy of microsecond, let's say 10 microsecond. And that's way good for seismic. You know, we use 1 millisecond sampling. But we know also that if we want to go to higher frequency sampling like EM, we need a better, maybe a higher accuracy. And we have a solution. We can actually use another type crystal. This is hopefully something we would do in the future. Would it be possible?
Then, I mean, this is actually a more general question. Aaron Sedilis, would it be possible to have the slides? Now, usually these get put up on MTNet. I don't know if what you and Alan discussed in this respect.
We could look at what's, I think some of these are already published, so I can look at it, what would be possible to share, yes. I think it's possible, most of it, but I won't promise you, so. I could say maybe 80% of it.
It's entirely your choice.
Yes.
What you want to have put up on the website. Just a quick comment, perhaps. Some years ago, about 12 years ago, I did magnetotellurics down a mine in Newfoundland, and we had cable to bring the GPS signal down. But even though the mine turned all the power off, it was pretty dangerous. They didn't like to do that. It turned all the power off. We still got hammered by 60 hertz. They were really quite poor. So I don't think you can think of doing MT down a mine. Control source EM maybe, but not MT.
One of the things we've been discussing with our people here, and I don't know if there is a solution, you know, if you guys can develop some EM tomography approach, like control source, as you were saying, maybe that opens up some possibilities.
Well, they do borehole to borehole tomography, EM tomography. So just a modified version of that. Sources and receive sources on the surface, receivers downhole, or vice versa.
Yeah.
Yeah. Sayed Forushani asked, well, thank you for your interesting talk. Have you ever tried to use the interfaces you got from seismic as sharp boundaries and EM and magnetic data inversions?
I think this is for you, Max, not for me. No, but I mean, you can. I think, you know, with cross-gradient approaches, let's say, boundaries in EM and magnetic. So I think possibly that's the simplest way to go. And that's if you look at for, you know, cross-gradient. We haven't, but I'm pretty sure there are people doing this, you know, or people here at Uppsala, they did it, of course, for MT and reflection seismic. And I think I don't see any reason you can't do it for magnetic.
Yes, and I mean, also thinking about, you know, I suppose you're talking about the work of Thomas Kaltscheuer and, oh, I forgot the name of his PhD student. But I mean, they didn't even go to a full cross gradient, but they just said, okay, the regularization at certain interfaces is reduced. So I think some of this can even be done with, if you want to, standard inversion packages, where you just trace the discontinuity and say, okay, we're not going to smooth across those. But yeah, I guess that's something that you can still sort of try in the future. Okay, somebody's looking for a job. So Salman Mirzayev, thanks for the informative presentation. Can someone join this project as a young professional?
So we just recently accepted 2 more MSc students working the project. Essentially, the project financially is finished. So, but because we have so much data, ideas develop as we speak, in a way, loose ground, we basically continue because we're also university anyway. So it's possible to join to do degree projects, but it's not possible to join to get financial benefits, to be straight.
Yeah, I mean, I think that's the standard problem, right? Usually at the end of these projects, you're left with a million things you would like to do and very little financial possibilities to actually do them. Or yeah, you rely on master students or maybe some PhD projects. Okay, another question coming in, Rajesh Vayavur. Have you done any 3D gravity constraint modeling?
At the Ludvika side, we also did gravity inversion, but only like, let's say, constrained way, not any joint inversion. I think that's maybe something one should do, and then I'm aware of algorithms available for this. We did that at Ludvika's side, but the gravity data, I think they were not so perfect. We got anomalies which we couldn't explain. And because these gravity data were collected in different campaigns, we realized maybe there was a little leveling problem. So that, actually one of the MSc students just mentioned he would be working on redoing this gravity modeling, constrained gravity model.
Yeah, and another question, again, Sayed Furushani. I think there's a restriction in your technique. It seems that the mineralized zones you can detect with your technique are the deposits with layered shapes. For instance, in Ludvika, the mineralized zone was a bauxite layer. Do you think it is possible to use your technique in more complicated cases? For example, interpreting the refractions with virtual records via GRM?
No, I mean, let's say if you got like, the case I showed from Canadian side, the response of that 10 million deposit is actually a diffraction. It's not even a reflection, it's a diffraction, but it's very, very beautiful diffraction. So it depends on the situation you got. So if the deposit has a complex geometry and let's say contrast, then of course you would not see it as layered reflections. And but it doesn't mean that your method would not work. So let's say if I did expect Lombardov would be a diffraction, so from surface measurement, of course, because then you have lower frequency as you go to, so if you go down above them, then your response would be reflection. So in a way, for example, this going in mind, it's one way to tackle this problem, because then you basically have higher frequencies. And so that's why you can, you can see the reflection better than diffraction sometimes. Yeah, so I would say maybe it's not fair to say you only see layered structure, but if you get layered structures, it's easier, of course, to see them. But then when you have complex features, then you will have a complex signature.
Yeah, and I suppose, while you acquire your data, you also then carefully think about the signatures in your data, and as you said, modify the method. It's not like you're going to just go straight into some migration if you know that there are issues there, right? And you carefully look and you think, okay, which bits of the data can I extract the most valuable information from, depending on the target, right?
And at Nev Shkurva, I did not have time to say it. At Nev Shkurva, our partners did another approach, and that was they built a 3D model. And I think I know some discoverers using the same approach. They built a 3D model based on everything they had, boreholes, petrophysics. And they forward calculated for both 1D TEM borehole, and I think also gravity. And there were places that the anomalies could not be explained. And they were very convinced that this could be a places to look a little bit, if there are any potential targets there. So that's another way. Sometimes, not seeing it could mean something.
Yes, yeah. Sort of, if your expectations aren't met, then that can mean that there's something interesting there. Okay. One more question from Syed Foroshani. How do you deal with the rate of losing vertical resolution by depth, which is not the same for seismic and EM data?
I'm assuming this is mag and gravity, huh? So yeah, I mean, you do lose resolution for anything, I would say, but some are faster decay than others, and so I don't think or geophysics has that kind of advantage yet, that you can't stop this resolution, because your earth material will first attenuate your signal, and then of course naturally your gravity field would decay, and mag the same. So how to deal with this is, if you can't do it on if let's say if you have done everything in the instrumentation, that means you have boosted your signal and then you have lowered your noise on the instrumentation side. I think the only way forward is to get closer to the target, and that means maybe in a borehole or maybe in a tunnel. Or if you can't do this, then you have to integrate everything now. And I don't think this would be something everyone can solve. This losing resolution is a natural.
Yeah, I mean, it's part of the physics of the
Yes.
of the methods. I guess the question is more about when you do a joint interpretation, or in my case, if you did a joint inversion, how to avoid that you sort of overinterpret maybe one of the data sets. But yeah, I think it's a tricky question that isn't fully answered yet. Johannes Stoll is asking, what is the EM noise floor of your VLF and/or RMT receiver in the upper frequency range, 10 to 100 kilohertz, when slung below the UAV?
I can only imagine our guys have measured this in the shielded room, let's say within the level of the ceiling, but I might actually be wrong, because if it's from the instrument, they have done the measurements. But now if it's out there, I must, Johannes, you need to contact Merdad, I guess, Bastani. So I'm pretty sure he would be best to tell you this. Some of the, in the slide I showed, some of the VLF frequencies were very clear, so it was, you could see them.
Yep.
I can also see questions and comments on the chat box, Max.
Okay, I didn't see those. I think that was the GPS question, and there was a bit of a, if you want, a side discussion between Merdad, Paula, Ralph, and a few others. Now, let me quickly check. Yeah, I think there's no sort of significant question there, at least as far as I can see. So yeah, to me it seems, well, there are a few people that thank you for your presentation, and yeah, on behalf of everybody, I'd like to thank you for that as well. And yeah, it seems like everything is answered now. So yeah, thanks again.
Thank you for having me.
Thanks everybody for attending. And yeah, if there are more in-depth discussion, I think it's also good to contact you directly. And yeah, with that, I'd like to close the EMinar for today and just remind you, next week it's going to be OSLAMP. So also probably also a bit of minerals there, but on a much bigger scale. So looking forward to that. Okay.
Thank you. Bye-bye. Have a
Thank
good
you
day.
and bye-bye.